So thank you coming for this Dream seminar. Our speaker today is Daniel Fremont, who is a PhD student here at Berkeley in the Logic group. And so Daniel is also starting his academic job search interview tour, and so this is also a good way for him to get feedback from all of you who are in the room. Before I let Daniel start, I just want to tell a little story about how he got started with his PhD topic. So about maybe 6 years ago, there's a research center starting up called the Terraswarm Research Center that Edward Lee, who's sitting here in the front row, was the director of. And at the kickoff meeting, I found myself sitting next to a professor of music, a late colleague, David Wessel, and we started talking about our common, our respective research areas and trying to find something in common. And David told me about an interesting area in computational music called improvisation, machine improvisation of music, which is getting computer programs to improvise the way humans do. And so we started to talk more about this over the next year and formalize this, and the formal methods person and me and Daniel came out, and we came up with a definition that has led to Daniel's thesis work. And one of the reasons we're having this talk here in the Dream seminar is because that really improvised path of research has led into the areas of embedded systems, cyber-physical systems, robotics, and IoT, which I think is very much the topic area for the seminar series. So without further delay, over to Daniel.
Thank you, Sanjit. Yes, so today I'm going to be talking about algorithmic improvisation and in particular applications to safe autonomy. The context for this work is really the rise in recent years of autonomous systems in safety critical applications. So self-driving cars and drones are obvious examples of that, but robots also, and even something like a smart grid increasingly is expected to operate with less and less and eventually no human supervision in a safety critical environment. So these types of systems are in desperate need of careful, rigorous design, but making them reliable is extremely difficult, as shown by examples like this one. So this was an interesting accident in 2017. Fortunately, no one was seriously injured. But what happened in this case was there was an Uber automated car on the left and a human turning right, the red car there. Neither could see the other because of these two lanes of stopped traffic there. And so the human turned left, probably should not have done that, but it caused this accident. So, of course, a company would now maybe like to go back and say, could we have designed the system differently to avoid this? Was it really the human's fault? What went into this accident? But there aren't really good tools right now to do a systematic exploration of possible designs, for example. And my work provides one of the first tools for this, and actually that's how we generated this simulation. So we'll come back to this later. But the big question is really, how can we build safe autonomous systems? And obviously, this is a question of real national interest because, for example, of the imminent deployment of self-driving cars, there are already some on the roads that aren't being supervised at all. And there's a lot of research going to this question, like the Assured Autonomy program, but I think it's still really an open question. And why is it so difficult to build these systems in a safe way? I think there are really three challenges that come together to create that problem. One is one we're familiar with in software for a long time, is just the complexity. So even an ordinary car, not a self-driving one these days, can have up to 150 million lines of code. So no individual person can keep track of all the interactions that are happening in that system. In addition, with things like a self-driving car, you now have an interaction with a highly complex environment, much more complex than that of ordinary software, and the software's decisions that are affecting agents in the real world, and it has to respond to that appropriately. And in response to these systems having such complicated environments, they're increasingly using machine learning. And that means we have very large models that are often uninterpretable. So you can't look at it and see why it made any particular decision. And as a result of all three of these, it's increasingly the case that even the designers of a system can only vaguely understand how it works, or more importantly, how it can go wrong. So the approach that I'm taking in this work to try to address the technical side of this issue is based in formal methods. So formal methods is an area where we try to use rigorous techniques to design, model, and analyze systems based on formal mathematical reasoning. So really the ideal case in formal methods is that you can actually prove correctness of a system. You model the system and you show mathematically that its behavior is always correct under all circumstances. And in practice, there are several reasons why you wouldn't be able to do that completely, but formal methods can still be helpful, as I hope I'll to show in this talk. For example, even in a case where you have a completely black box system and you're just doing testing, you can still use some of these techniques to do more principled, intelligent forms of testing. So to make this a little concrete, let me talk about a bunch of different ways you can apply formal methods to an autonomous system. So if you have something like a drone or a self-driving car, what are the different components in this system? Well, you've got sensors, which are giving you some information about the environment. You might also have communication happening between other agents in the system. And then in the computer for these systems, you have various types of things going on. For example, you might be using machine learning to analyze your sensor data and decide what is happening in the world. On top of that, you might be doing some probabilistic inference, saying, okay, I know that there's a person here and a person there. What is the most likely action that the person will take next, given what I've seen them doing so far? And then on top of that, you have some kind of task planning going on. So saying, what decisions should I take in order to achieve my goals? And this has to work in a reactive way because there's some part of the environment, like human agents, that you can't predict completely. And you need to be able to respond to whatever they actually end up doing. So formal methods can help with all these different components of the system. So for example, I've done work on controller synthesis, generating a correct by construction task planner, say, that can handle all kinds of environments and is always guaranteed to satisfy certain formal specifications. For probabilistic inference, I've done work on model counting, which can be used to give stronger guarantees on the accuracy of the inference than you would get from just like a MCMC type method, for example. If you've got communication happening, you might be worried about privacy issues, say. Like maybe even if the communication is encrypted, the amount of communication you're doing or the timing might leak some private information. And I've worked on tools that can quantify that information leakage and tell you whether you need to use countermeasures, for example. If you want to do testing, say, of this perception system, you could generate environments at random and see how well the system does. And I've done work on uniform sampling from constraints. So you have constraints describing what type of environment you want, and you can use these algorithms to generate solutions to those constraints, random solutions. And similarly, you can use that kind of idea to generate random human-like behaviors. If you want to test how well your system does, you need models of the human agents, and you can use this technology for that also. And underlying a lot of these different pieces are constraint solvers. So I've also done some work on just trying to understand why do SAT solvers work well in some cases, even though it's solving an NP-hard problem, and when do they not work. So in this talk, I'm just going to talk about a few projects, these two, and an ongoing project called SCENIC, which is a domain-specific language to design and analyze cyber-physical systems. And I'm talking about these three in particular because they all, at a high level, are instances of the same kind of general problem, which is constrained random generation. So for example, if you're generating a controller for a robot that's supposed to explore some space, you might want it to use randomness to explore that space in an unbiased way, but all the trajectories that you generate should be safe. So you need a way to generate a randomized controller that's still correct by construction. If you are doing human modeling, you'd like to have realistic models of human behavior. Those are also going to have randomness because humans' behavior is randomness, but you'd like to impose constraints on those. And finally, if you're doing training and analysis of a system in simulation, you might want to generate training sets or test sets that are tunable. So you can say, how well does my system do in a particular environment, but also diverse. So if you're doing training, you don't overfit to anything in particular. And all three of these problems can be viewed as instances of algorithmic improvisation, which is the core problem of my work, which I'll be talking about in this talk. So before I get into the definition of the problem, let me just motivate a little bit more about why randomness is such an important aspect of all of these problems. So one reason you could use randomness is just to get variety. As I said, let's say you want to generate a test generator or a training set generator for an object detecting neural network. It takes images like this and it puts a bounding box around each car. So the task could be something like generate images of bumper-to-bumper traffic. The issue is that's a huge space. These three images are very different from each other, but they all could reasonably be described as bumper-to-bumper traffic. But randomness lets you cover that space evenly. Another reason to use randomness is realism. So let's say you're designing a lighting controller for a house that turns the lights on and off in the various rooms to make it look like you're still at home when you're on vacation, say. So if you just fit a deterministic model to the human behavior over the past month, say, that would be unrealistic because human behavior is intrinsically random. So using some techniques I'll talk about in this paper, we generated a controller that's producing all of the traces here, which are power consumption traces, except for the first three. Those are human traces, and the rest are ones we improvised using our techniques. And a final example, very different area, is if you, let's say you had a surveillance robot that you want to patrol some area, visiting a bunch of important locations. If you did that by some fixed route, it would be highly predictable. So someone could know if you're on this end of the museum every night at 2 a.m., we should break in on the other end. But if you use a random route, it can make that your future location harder to predict. So in all of these systems, randomness was really essential for the system to be operating correctly. But at the same time, they have to satisfy formal specifications. So in the lighting control example, you might want to make sure that the controller doesn't use too much electricity over the time that you're gone. In the test generation case, you don't want to generate useless data, like ones where cars are through each other, for instance. That would not be a realistic test or training point. And of course, if you're doing robotic planning, you have safety constraints, like you should not collide with another robot moving around in the same space. So really the question is, how can you design a system that has random behavior, but is still controlled, still satisfies various important guarantees? And that's what algorithmic improvisation is all about. It's a framework for automatically synthesizing systems, which could be reactive, that have random behavior but formal guarantees. So there are really two types of guarantees. One is the usual one in correct by construction synthesis, guaranteed safety. So you can impose some constraints, and those are going to be guaranteed to be satisfied no matter what happens. The new thing is really a guarantee of randomness, that the system also will have a certain amount of diversity or variety in its behavior. And that's the new thing here. Having randomness is part of the specification. And that means that solving this problem requires fundamentally different techniques from work, say, in reactive synthesis that people have looked at already. But this problem turns out to be kind of an interesting one at the confluence of several different areas. From formal methods, we are using notions of specification and also constraint solving technology. From theory, we use automata theory in some of our algorithms, and also, of course, these algorithms are all randomized using different approximation algorithms from randomized algorithms. And from the PL side, we're also, as you'll see later, we can also use probabilistic programming languages as a form of constraint to specify certain desired properties of these systems. So, just to give you an outline of the talk, I'm first going to talk a little bit about the core theoretical problem in this work, which we call control improvisation. Then I'll tell you a little bit about the theory of that problem, in particular the efficient algorithms that we've come up with and hardness results for the other cases. And then I'll talk in detail about one application, namely this one of analyzing perception systems, and then give you some ideas about where we're going in future work. Okay, so to start with this. So here's a kind of a motivating example, this robotic surveillance one. So here's an actual experiment we did that this is being played back at high speed, where this drone is patrolling these various different white locations. The big one on the left is supposed to represent a charging station that it has to go back to periodically. And the task, again, is to visit these places in a kind of random way. And here what is happening is we're using our algorithms to do the high-level planning. That's then going over to a colleague of who's right over there to do lower-level planning, and then going to a very low-level controller that actually reasons about the dynamics of the system. And then it was run on a test bed, an actual drone test bed at UPenn. So what are you trying to do in a task like this? So we want to patrol an area in an unpredictable way. There are various types of specifications that we might want for that system. So for example, visit each location sufficiently often, obviously. We might also want to have inefficiency constraints. So for instance, take a route close to the shortest one. You could, by adding enough randomness, take some arbitrarily wiggly route, and you might want to rule that out for efficiency reasons. And of course, we don't want you to always take the same route. We want it to be somehow unpredictable. So these are really three different types of constraints. The first is what I call a hard constraint. This is something that has to be true always. The second is a soft constraint. It's kind of tunable. You can say it only has to be true to a certain extent. And finally, the last property is a property of the distribution, saying that no particular behavior happens too frequently. And we'll see that in other tasks, we get those same types of constraints. So for example, in this task of generating test images for the neural network, we might have realism constraints, like objects should not intersect. We might also have a constraint to say, well, this system is going to be operating in the real world. We would like the images we generate to somehow reflect the way that people drive in practice. And of course, we want to generate a diverse set of images. So again, these are these three different types of constraints. So in these two applications, and in a bunch of other ones, like music improvisation that Sanjit mentioned, and software fuzz testing and several others, you're trying to generate sequences or data subject to three kinds of constraints. A hard constraint, which everything you generate has to satisfy. A soft constraint, which most things you generate have to satisfy. And a randomness constraint saying that nothing is generated too frequently. And control improvisation is just a precisely defined theoretical problem that captures these three requirements. And the reason we needed to define a new problem for this is that really nothing in the literature so far captured all of the different aspects at once. So for instance, in work in computer music with factor oracles allows you to kind of enforce a soft constraint. You can construct variations on things, but there's no way to enforce a hard constraint that has to be true all of the time. And that's similar to techniques in mutational fuzz testing, where you generate variations on files. Conversely, there's work on uniform sampling from constraints, where you can enforce some specification and say that has to hold all the time. But there isn't a way to enforce a soft constraint or do that in a reactive way. And that's similar to work in generative fuzz testing, where you might generate random files from a grammar, say. Then along a different axis, there's work in reactive synthesis, where you can generate a controller that's guaranteed to be correct under all environments. So you get a hard constraint, and it's reactive, but there's no way to do that randomly. You might just get a deterministic policy out of this. And control improvisation combines all four of these. Okay, so let me work towards actually defining it formally. There are a few components to the definition, so I'm going to use this motivating example of the patrolling drone. So we have a drone in the bottom left that's moving around in this grid world. We want it to visit the 4 circles, potentially avoiding collisions with some other robot, the other triangle. So we're going to say we're generating sequences of some fixed length n, just to simplify things. We can actually handle any range of lengths, but it has to be bounded, from a finite alphabet, which will here be, for example, the actions the robot can take. So north, south, east, west. And I'll say we're generating things of length 30 for this example. The hard constraints will be given by a specification h. A specification can be any way of specifying a property. So it could be an explicit set, a Boolean formula, an automaton, anything like that. The complexity of the problem will change with that. So here our hard constraint could be visit all 4 circles, avoiding collisions with the other robot. And the soft constraints are given by another specification S. So here it could be, for example, don't redundantly visit one of the 4 places. Okay. So now I'll define a few sets using those. So if this is the space of all sequences that you could generate of those actions, this contains behaviors that we don't want. So for example, a trace where our robot runs into some other robot. So I'm going to cut out part of this space, I, which are the improvisations. These are the traces that satisfy the hard constraint, H. So for example, in here we would have this trace that successfully visits all 4 locations without colliding. And then the admissible improvisations are those that additionally satisfy the soft constraint. So for example, this trajectory here doesn't satisfy the soft constraint because we visited that location twice. Here we visited them exactly once, we avoided collisions, so that satisfies both the hard and the soft constraint. Okay, so now given these sets I and A, I can define the control improvisation problem. So given those sets and some parameters, which we'll see where they come in just a second, a distribution on words is an improvising distribution if it satisfies three properties. The hard constraint says that you satisfy the hard constraint with probability 1. So you always get an improvisation, something in this set I. The soft constraint is very similar. It says that you get something in A, satisfying the soft constraint, at least 1 minus epsilon of the time. So the parameter epsilon here is controlling how tight the soft constraint is. And finally, for any word, any improvisation, its probability has to be between lambda and rho. So you can, if you want to ensure that nothing is generated too frequently, you can decrease rho. If you want to ensure that something is generated with at least some probability, you can increase lambda. In this talk, I'm just going to set lambda equals 0 everywhere to simplify things. So given all of that, the control improvisation instance is feasible if one of these distributions exists. And then what we really want is an algorithm that samples from one of these distributions, and we call that an improviser. So to give an example, suppose we just had 3 traces in A and 2 in the improvisations here that aren't admissible. Of course, in the drone example, we have thousands and thousands. But suppose we just had those 5. Then if we set epsilon and rho equal to 1/4, here's an improvising distribution. Return each of those 3 in the corner with probability 1/4 each, and each of the other 2 with probability 1/8. Then we satisfy the hard constraint because we always generate things in I. We satisfy the soft constraint because 3/4 of the time you get something in A, and we had epsilon equals 1/4. And you satisfy the randomness requirement because nothing is generated with probability greater than 1/4, which was rho. So that was the non-reactive version. Definition is the non-reactive version where you generate a trace all at once. The reactive version is quite similar. There are just a few changes. So here, imagine now that other robot, we can't control it. It's adversarial, and we want to make sure that we are always safe no matter what it does. So now the system and the adversary alternate picking symbols to generate the combined trace. So it's a 2-player game. We still have the hard, the soft, and the randomness constraints, but we require that they hold against every adversary. So we would assume, we would have to require, rather, that no matter what the adversary does, we don't generate any behavior with probability greater than rho, for example. And then the improviser becomes an improvising strategy. So it takes in what the adversary has done so far and computes the next move. And once you make those changes to the definition, you have a way to do reactive synthesis in a randomized way, at least for bounded time, which is adequate for example, robotics applications like this one. So just to give you an example of that, here are some simulations I ran on the right where the improviser is controlling the black line robot, and I have an adversary, the blue line, dashed line, which I've had in these 4 runs move in the same way in all 4 runs, so that you can see that the improviser is making different random choices in each run. But in all of those, it's satisfying the hard constraint, so it's visiting the 4 circles. There's also a soft constraint saying 3/4 of the time we don't redundantly visit a location, and you can see in most of these it's satisfying that also. And the randomness requirement here that I used was actually use the smallest feasible rho, so kind of the maximally randomized strategy, and our algorithms can actually compute that for you. So here, it turns out this controller won't use any particular trajectory with probability greater than 1 in a trillion. All right, so that was the definition of control improvisation. Now let me talk a little bit about the theory of how we solve this problem. So the most basic question is, when is it possible to solve the problem? So when does one of those distributions satisfying those 3 properties exist? So it turns out that with lambda equals 0, feasibility just requires these sets I and A to be large enough. So here's the statement. It just says an instance is feasible if and only if these 2 inequalities are satisfied. And I'll give you an idea of the proof. It's pretty easy to see that these are actually necessary because, for instance, imagine that there were fewer than 1/rho improvisations. Then even if you assigned all of them the maximum probability you're allowed to rho, it wouldn't add up to 1. So that would not be possible. And just to formalize that, suppose we have an improvising distribution D, then let's assign rho to every element of I. That's at least as much as assigning the actual probability to each element of I, because the probability has to be at most rho. But that's just the probability of getting something in I under this distribution. And by the hard constraint, that has to be 1. You have to always get something satisfying in the set I. That's an improvisation. So the set I has to be at least that large. By exactly analogous logic, if we assign rho to each element of A, that's at least as much as the probability of getting something in A. And by the soft constraint, that has to be at least 1 minus epsilon. So A has to be at least that large. Then to show that these are actually sufficient, suppose those inequalities hold, the crucial thing is this quantity. So the idea here is this is going to be the probability that we generate something that's an improvisation but is not admissible. The idea is we try to assign the maximum probability rho to each element in A. That might end up, there might not be enough probability to do that. So if rho times alpha is greater than 1, you can't do that. So then we clamp this to 0. So we'll say we'll assign no probability to the inadmissible improvisations, and we'll just spread it uniformly over A. So if we do this, you get a distribution. The hard constraint is trivially satisfied because we're always generating things from I, either from A, which is a subset of it, or from I minus A. And the soft and randomness constraints, you need a little case analysis, but if you just check all the different possibilities here, you see that always you get something in A with probability at least 1 minus epsilon, and you don't generate anything with probability greater than rho. So this indeed gives you a improvising distribution. So that's the simplest kind of result, just showing when can one of these distributions exist. But what we really want is an algorithm that computes improvisers. Given an instance, it generates an improviser for you. So it tells you how to sample from this distribution. And in particular, we'd like an efficient one of those. So we say a polynomial time improvisation scheme, that's our name for a synthesis algorithm in this sense, for a class of problems, is an algorithm such that given an instance in the class, it returns you an improviser if the instance is feasible, and otherwise it returns some symbol saying, can't do it, there is no solution. And both the scheme and the improvisers it generates run in polynomial time in the size of the original instance. So, along the lines of that proof I just showed, we can actually construct a general way of doing this for any kind of specification that supports a few operations. So if you can intersect and take the difference of two of them, restrict one to a given length, and more interestingly, count the number of words satisfying a specification, and uniformly sample from those words. And notice these can be highly non-trivial operations. So for example, imagine the specification is a Boolean formula. Then even finding one solution isn't hard, let alone counting the number of them. So whether or not you can do this depends on what type of specification you have. But if you can do all of the, so for example, for Boolean formulas, you can apply some of my other work on model counting using constraint solvers. But suppose you can do all of these. If you can do them in polynomial time, then there's a polynomial time improvisation scheme. And if you can do them in some higher class, there's also a scheme in that class. And it works in a very simple way. You first construct specifications for these three sets, I, A, and I minus A, using intersection, difference, and restriction. You count them using counting, and you check the inequalities we just saw. If those are violated, then there's no solution, so you return failure. Otherwise, you sample from the admissible improvisations or the inadmissible ones with the right probabilities using that epsilon opt I showed on the previous slide. And this gives you an improvising distribution. Okay. So using this scheme, we can instantiate this in cases where we can implement all of those different operations and get some algorithms. So in particular, we get polynomial time improvisation schemes for deterministic finite automata, which we've used, for instance, in the music and robotic planning examples. So like the specs for that drone can be written down as an automaton. Another interesting case is that of unambiguous context-free grammars. So this is useful for fuzz testing, for instance, where you could have a grammar for a file format and you want to generate tests from that. So we get a picture like this where in those cases we get polynomial time algorithms. More generally, it's sharp P equivalent. That's a class of counting problems. And an interesting thing is if you have two unambiguous grammars, it becomes as hard as the general case. And then for harder specifications, we have some results. For example, with Boolean formulas, we have an algorithm that can still solve the problem approximately using constraint solving work. Okay, so this was again in the non-reactive case. If it's reactive, feasibility again reduces to counting. Now there have to be sufficiently many ways to win the two-player game. So you can imagine, normally in reactive synthesis, you just need a winning strategy in this game. Here, imagine that there was only one way to win. So the adversary could force you at every step to only make one choice. Anything else would be unsafe. Then you wouldn't be able to do that in a random way. You just have to do that one thing. So here, there have to be sufficiently many different ways to win the game. And it turns out that the result looks very similar to what we had before. We have the exact same inequalities. It's just we have a new notion of the size of these sets, which we call width. This counts the number of winning plays, essentially, minimized over all adversaries. So here's the formal definition. Let me just tell you what the notation is here. So sigma is running over choices for us, for the improviser. Tau is running over the adversary strategy. This P just means the probability of obtaining the trace W given those choices of strategies. And so this term just represents the number of traces with positive probability. So these are the behaviors, the combined behaviors of the system that are possible given the two strategies. And now the adversary is trying to minimize that, so to make as few choices available as possible, and we're trying to maximize that. So that's this width. And it turns out, as we saw on the previous slide, if the width of I and A is sufficiently large, you can generate an improviser. I only give you a brief idea of how the proof goes because it turns out to be a lot more complicated than the non-reactive case. In particular, an interesting point from the game theory side is that even in a game like a reachability game, where in normal reactive synthesis, you can solve that in a completely memoryless way. Just given where you are now, you can look in a table to decide what to do next. You don't have to maintain any memory. It turns out here, the interaction of the hard, the soft, and the randomness constraints means that in some cases where classically, without randomness, you don't need memory, here you have to have memory. So that means the strategy is a little bit more involved, but it's a kind of random walk. So here, this diagram is showing an unrolling of a game where the number is showing the width at that position. So in these states here, the width is 1 because there's one way to win. You're already in a winning state. Whereas here, at an adversary-controlled state, it's 0 because they can send you off there and you lose. So the way the strategy works is essentially if you're at a state here and there are 4 ways to win, broken down 1, 2, and 1, you do a random walk splitting based on these weights. So you would go up there with probability 1/4, 2/4, 1/4. That would be completely memoryless, so we do something a little more complicated on top of that, but that gives you a general idea. And as this diagram sort of shows, you can actually compute these widths by dynamic programming in some important cases, even if there's potentially exponentially many states. And that yields efficient algorithms for this. So again, we get an efficient scheme for deterministic finite automata specifications, and that includes things like reachability and safety games as a special case. You can encode those. For temporal logics, like linear temporal logic, popular in reactive synthesis, the problem is p-space equivalent, but actually even without the randomness, in a finite window, it's already p-space equivalent. So this shows that adding randomness in this way doesn't increase the complexity, at least in a coarse-grained sense. Right. Yeah, so this is basically what I wanted to say on the theory of control improvisations. So now let me talk about an application of this to designing and analyzing perception systems. So the motivating example, I'll come back to this picture we saw before, is that of a self-driving car. So I'm going to call the environment configuration here, so the position of all the cars, the orientation and so forth, the scene. So this isn't the input to the sensor. So it's not the RGB values in the image. This is a high-level description of what the environment is like. The problem here is that collecting examples of real-world scenes is expensive. You can drive around and take pictures, but to get these high-level descriptions, you would need to do scene understanding and figure out where the cars or all the other objects were in the scene. But it's very useful to have realistic scenes because you can use them for training. You have the ground truth. You know where everything is. And you can also use them for testing. So why is it difficult to generate realistic scenes? The issue is that it's easy to sample random scenes, but they may not be meaningful because the scene space is very large and unstructured. So for a single vehicle, you might have lots of parameters like where is it, what type of car is it, what color, and so forth. If you have a lot of cars, these add up. And it's unstructured. If you just randomly plunked a bunch of cars down on the road, that would not give you a realistic configuration. Some would be pointing backwards, some would be just laid out in a completely random way, whereas realistic scenes have complex geometric constraints. So people tend to drive in lanes, for example. Sometimes they deviate, but generally they drive in lanes. Furthermore, you might be interested in particular types of scenes, like highway traffic. And then you would want to add more constraints, saying, I only want scenes of this particular type. So you can see that this is another instance of control improvisation. You want to generate random things subject to constraints. But how can we formalize these type of constraints? So again, we have hard and soft constraints like I talked about before. So for example, objects should not intersect. That's a hard constraint. You might have a soft constraint like if you want to generate a training set and you want to make sure your system works at night, you would like to make sure that night is adequately represented in the training set. So you might say 20% of the images should be at night. However, there are some types of specifications that don't really fit into what I described before. For example, in this bumper-to-bumper traffic case, you might have collected data on how close people tend to drive to each other. And you might want to say the gap between two successive cars should follow this particular distribution. That requires finer control over the distribution than the definition I gave before. So we need a different way of dealing with that. And we argue that a natural way to encode that type of specification is using a probabilistic programming language. So that's what we've done in this project. We've defined SCENIC, which is a scenario description language. Our program in SCENIC defines a distribution over scenes. So for example, we wrote a SCENIC program that's supposed to represent bumper-to-bumper traffic. And that describes a distribution. If you sample from that, you get different scenes that are instances of bumper-to-bumper traffic, and that's what's being shown here. The nice thing about SCENIC is that it provides readable, concise syntax for common geometric relationships, so that allows you to express a complicated type of scene, like this bumper-to-bumper one with, I think, 12 cars, in only a few lines. So this is like 20 lines. But moreover, the syntax of SCENIC enables domain-specific sampling techniques based on configuration spaces that make the sampling more efficient than with a general probabilistic programming language. And you can also impose declarative hard and soft constraints. So you can say, lay things out in this way and require globally that, you know, these two cars are at least this distance from each other, for example. So these correspond to the hard constraints in control improvisation as we saw before. And now we have control over distributions. That's kind of like a more general randomness requirement. So there's a lot of related work we're drawing on here. So one, in probabilistic programming languages, SCENIC semantics is that of a standard imperative PPL, so I won't talk about that more. Those type of languages have been used as generative models of graphics, although not for test generation as far as we know. The main difference in SCENIC is the domain specificity. There's also work in computer graphics on scene synthesis from examples or grammars, and in machine learning on data augmentation and generation. And the main difference here is that SCENIC gives you more control because you can, for example, apply global constraints in a way that you wouldn't be able to do in a shape grammar. And it's easier to use, we argue. Okay, so let me give you an actual example. So suppose we want to write a scenario for a badly parked car. So the first thing we're going to do is we need to import into our scenario the basic information about the workspace. Where are the roads and things like that. Our language doesn't have anything built in. It's not specific to driving at all. So what I'm doing in the first line of the program here is from a package for our case study in this video game, GTA, which people have used for autonomous driving experiments. I'm importing the concept of what a car is. So this is a class defining, you know, what these objects are, how big they are, that kind of thing. The curb, which is a region, that's the red line in this diagram, showing where in the world the curbs are. And road direction is a vector field saying at every point in space what is the nominal driving direction. So like at this point on the road you should probably drive that way. At this point you should probably drive that way or that way. Then I'm creating the ego car, so the car that's going to be the reference for the camera. That's the car here. This is showing the view cone. Notice I haven't said anything about where this car is, what its color is, and so forth. So we're using the default distributions, the priors, in the car class. So for example, the prior for a car's position is that it's uniformly over the road, but not off-road somewhere, for example. Now we're going to pick a spot for the parked car, the second car. The way I'm going to do that is in a couple steps. So I'm taking the curb, this red line there, and I'm passing it to the function visible. So that's going to restrict it to the part of the curb that's within the view cone. So like this part is not. And then I'm going to pick a point on that region, say this point, and that means a uniformly random point. So I haven't said which point, so it could be anywhere on that black line. We pick one uniformly at random, it could be there, for example. Then I'm going to pick the angle for this car to be parked at. This notation here means the uniform distribution over that interval. So I want it to be between, say, 10 and 20 degrees, so it's not parked lined up with the road, but it's a little bit off, times 1 or negative 1, so to left or right. Okay, and now I can start creating this car. So I'm going to take that spot, parking spot, and I'm offsetting it by a vector. So this is the Smalltalk vector syntax, which says negative half a meter to the left and 0 up or down. So that means take that spot and offset it half a meter to the left in its local coordinate system. So not half a meter west, but relative to this point on the curb. And then I'm going to create the car to the left of that. So I don't want the car to be centered there. I want it to be to the left of that. Facing that funny angle, not in the global coordinate system, but relative to the road direction. So this left of and facing is a construct in Scenic called a specifier that lets you define things in a variety of different ways and can work out dependencies. So for example, here, the road direction defines a different direction at every point in space, but Scenic deduces here that you mean the position of this particular car, so because you're in the middle of defining it, so it works out that it has to sample the location of the car first before evaluating this bad angle relative to road direction. Okay. And notice I haven't imposed any hard constraints here. The Scenic has syntax to do that, but actually it already has some built in which are sufficient for this case. For example, it requires that two objects cannot intersect each other by default. So this is a complete Scenic program. If you put this through the tool, you get samples from the distribution, and then if you put those into a simulator, you can generate data. So for example, here, we put them into that video game, and we can render images like this one. And indeed, there's a car by the curb, but it's at a bit of a funny angle. But you can see you can get very different images because we have left a lot of stuff unconstrained, like how far away the car is from the camera, what the weather is, this kind of thing. Okay, so that was a simple example, but we can define much more complicated things like the bumper-to-bumper one I showed before. Another interesting thing in Scenic, why we have our own language for this, is that we can use domain-specific sampling techniques. And just to give you a very rough idea of how those work, we prune infeasible parts of the space by dilating polygons, for example. So given that we know we're talking about geometry, we can prune away some parts of the space. So for example, if you require that the distance from the ego to some other car, the taxi, is at most 5 meters, and the relative heading of it is within 15 and 45 degrees. So you want a taxi that's close to you but is turning, so it's not facing the same way you are. Our tool can use that to greatly restrict the space. So here's a map of part of Berkeley, actually. The scenario defines this whole map, but our tool can work out that the only possible places to get a configuration like this are the green areas here. So essentially near intersections, because that's where the taxi could be turning. So what can you actually do with this language? There are a bunch of different applications. For example, exploring system performance by generating specialized test sets for different conditions. So just to show that this isn't all about cars, here's a proof of concept we did for testing a motion planning algorithm for a robot that has to climb over rocks. This scenario produces an interesting case for it where there's kind of a bottleneck between those pipes. Another application is debugging a known failure. So here's an image we generated where for some reason the neural network thinks this is 3 different cars. So now you want to know why. You can use our language to write new programs generalizing that specific counterexample in a lot of different directions. So like, would this counterexample go away if you change the model of the car or if you added a little bit of noise to its position? And then you can work out what the root cause was. So in the case of this one, we found out the root cause was just distance to the camera, actually. The training set didn't have enough images of cars close to the camera. We wrote a new scenario generating those, retrained and fixed the bug without overfitting to that particular counterexample. The last application, which I'll talk about in a little more detail, is designing more effective training sets by training on hard cases. So here's a hard case for this car detection task, where one car is partly blocking your view of another. So we wrote a Scenic program that generates that type of scene, so like these images here, where one car is partially occluded. And then what we show is that we can design a better training set by picking those images out. So what we first did is we trained on data from the same simulator collected by another group. It's another data set that they obtained by just driving around inside that simulated world and taking screenshots periodically. So if we train on that data set, which I'll call X matrix, and test on the same kind of data, you get some numbers for precision and recall. Absolute values don't matter. The point is, if you test it on our overlapping images, the precision is significantly worse because it has trouble localizing that car in the back. The recall is actually a lot better because the overlapping images only have 2 cars, whereas the general data set can have more. So now what we did is we retrained the network on a training set of the same size, but now we replaced 5% of those general images with the specific overlapping images. As you would expect, performance on the overlapping images goes way up, but the important thing is that performance on the original data set doesn't get worse. In fact, it actually got a little bit better. So here we're able to improve performance in the hard case without increasing the size of the training set by designing it in a more clever way. Not taking completely random images by driving around, but by emphasizing this hard case of overlapping cars. Okay, so let me just conclude with some directions for future work. A lot of the work that I've done has come into a bunch of several different layers. So a lot of it is at the bottom level here of core theory and algorithms for all sorts of different applications. On top of that, I've worked on languages and modeling like the SCENIC language that finally enables techniques for design, verification, and testing. So I think there's future work to be done in all three of these levels by extending algorithmic improvisation. So because it's a fundamentally new problem in computer science, there are rich possibilities in all levels. So in the application level, intelligent test generation, I'll talk about a bit. At the language level, new environment modeling formalisms. And at the theory level, a generalized theory of control improvisation and theory for verifying systems with machine learning components. Okay, so for intelligent test generation, the idea is, like SCENIC, we use a DSL to write a test scenario that the human can use to guide the test generator. The challenge is, can we use information about how that test went or other kinds of analysis of the system to get the test generator to produce more effective tests? And one project I've done along these lines is called Contest, which is a testing tool for ordinary software, just C programs, where you use a scenario language in conjunction with symbolic execution. So that's a formal automated analysis of a computer program. And we've used that to find bugs in the Mars 2020 rover flight software. Another type of application at the language level is new environment modeling formalisms. So in particular, the examples with SCENIC I showed before were all perception. If you'd like to analyze controllers, then you would like to generate environments where there's dynamics. Things are changing over time. And that's actually where this simulation I showed you before was. We're using SCENIC to generate initial configurations for simulations. So notice here, the accident didn't happen. There was a variation on that accident where the timing was slightly different and it didn't happen, whereas here the accident does happen. So using SCENIC, you could do fuzz testing in this way of these type of controllers. To generate specifications and environments to test a system, you can also use it to create human models, as I described before. There's been some work along these lines already by the Caltech group in the Vehicle project, generating a human-like lane change controller using control improvisation. And of course, because these specifications are going to be very complicated for systems like cars, we would need techniques for learning them from data. Okay, I see I'm almost out of time, so let me just skip this. Essentially, we can have some more generalized forms of control improvisation that would be useful for different applications. And finally, for verifying systems with ML components, I talked about doing simulation-based testing and generating images like this and seeing how well the system behaves. Of course, an issue there is, do simulation results actually mean anything in reality? And I think there is some hope that we can try to prove, we can give guarantees of that kind using recent work on proving networks robust. So what you could try to do is do large-scale testing in simulation and then prove that the system is robust to kind of the gap between simulation and reality. So for example, show that the network doesn't care about details of the rendering in the particular simulation. If you changed pixel values, so the rendering was slightly different, it wouldn't affect the controller. Okay. So to wrap up, algorithmic improvisation is a framework for randomized synthesis with a lot of different applications. I had time to talk about just a few in this talk, in particular applications to safe autonomy, generating controllers and synthetic data for training and testing. The bigger picture question that I hope I've showed is that formal methods can contribute in many ways to the design, verification, and testing of these type of systems. I'd like to thank all my collaborators on all these projects and our funding sources. And just to leave you with a picture, I think there are good prospects for a rigorous design process based on algorithmic improvisation and other types of automated formal analysis that would ensure the safety of intelligent autonomous systems. Thank you.